Hello, learners. Today, I shall discuss the next lesson of our lesson 2 to make you understand in a better way. I would like to share some presentation with you during my lecture session. So I want to share my screen. We first discuss the objectives of this lesson, point out these objectives. This lesson has been developed with a view to achieve the following objectives: basic concepts of programming, concepts of different kinds of system software required for the execution process of a program, concepts of structured programs, standard program logic structures, concepts of unstructured programs, illustrative examples to demonstrate the sequence logic structure. Basics of programming. R provides an interpreted programming environment. To understand this, let us have a brief discussion on programming basics. We know that a computer program is a sequential set of instructions in a programming language which is usually executed in a batch mode with a view to generate some desired output by a computer on the basis of some appropriate input. The instructions of a program are written one after another in the order of execution following some predefined algorithm by using a text editor and then saved in a file. This unit of a computer program is called a source program. The source program is then translated in its equivalent machine language form by using either an assembler for instructions in an assembly language or a compiler for instructions in a high-level language or HLL. As the case may be, to generate the translated version of the source program, which is called an object module or object program. The object program is then linked with the standard library routines, leading to the formation of an executable module by using a system software called a linker. The executable module can then be loaded in the computer's main memory any number of times for execution of the steps specified in the program, called program logic, by using a system software called loader. Inputs are then supplied if required and output is obtained in a successful run. The translator that we use for assembling or compilation understands only the syntax of the language. So it shows a message, no errors or warnings when it finds no syntactic error in the instructions of a program. However, the program may contain semantic errors, also called logical errors, which are understood by the computer, and on facing such an error, the machine terminates the program, showing some message. Such a program is to be checked again, starting from the source code, and the steps described above are to be followed again to create the executable code set. This process is followed in assembly language programming and in some high-level language programming like COBOL, C, etc. There is an alternative translator called interpreter that translates an instruction in programming language by checking its syntax as well as semantics and then executes the instruction immediately if the instruction is found to be correct in both respects to generate the output meant by the instruction. Thus, an interpreter handles a program through translation and execution of the instruction at a time until it reaches the end of the set of codes submitted. R, being a scripting language, provides us with an environment where each entered instruction is taken care of by the inbuilt command interpreter for immediate translation and followed by its execution. Such an environment is being referred to as interpreted programming environment. So the environment readily provided by R is an interactive one. This enables us to follow the incremental development process in which we can write only one instruction at a time, test it, and go for writing the next statement if the preceding one is found to be correct. However, in R, we can also perform batch processing of instructions where we can write all the requisite instructions to implement some algorithm using an inbuilt editor in the system, which are then submitted to the R interpreter, either partly or wholly, for the desired interpretation of the statements one by one till the end of the batch if no errors are encountered in any step. A complete set of instructions implementing an algorithm is termed as an R script. By the definition, we can have a single instruction also to form an R script if it can implement an algorithm. Hence, R can be used both as an interactive as well as a batch processing programming language. In an interactive mode, we see the non-procedural feature of R, in which we need not state how to do something, but what to do. Such computer languages are known as fourth generation languages. On the contrary, in a batch mode of programming, we specify the tasks to be performed sequentially, one after another, to achieve a particular objective. We state how to do something. This is the basic feature of a procedural language, which is also known as third generation language or 3GL. So R was created as a computer language, with both the features of 3GL as well as 4GL. We will explore first the 3GL features of R in a few lessons now. Later, we will also study the 4GL features in a greater detail in the following lessons. The 3GL features of R can also be utilized to develop structured programs or systems, which is very essential and desirable form of programming technique for all types of data processing, including statistical analysis to data analytics and data mining, apart from normal data processing activities. A program is said to be structured program if it is easily readable, easily understandable, and easily modifiable. Our challenge is to develop such a program which is easily readable, easily understandable, and easily modifiable. Structured programs can be developed by breaking down the activities into smaller units of tasks for performing a specific function. Each such unit is called a module. Each of such modules should only contain statements or instructions formed with only one or more of four standard logic structures, namely sequence, selection, iteration, and case. This is why structured programs are also called modular programs, and the programming technique is known as modular programming. This is a top-down approach to program development that can materialize the characteristics of a structured program. The programs which lack the features of a structured program are known as unstructured or spaghetti bowl programs. Programs particularly consisting of instructions like goto for unconditional transfer of controls are known as unstructured or spaghetti bowl programs, because such instructions make the programs a weird set of instructions that cannot be debugged easily, and they lose the goodness of readability and understandability. We shall study R by defining and implementing the logic structures of structured programming one by one in the subsequent lessons. First, we shall consider the sequence logic structure. This logic structure includes a simple input process output statements. There may or may not be any input statement, but there should be one or more processing or output statements. The logic structure can be depicted pictorially as shown below. After the start, inputs may be taken, inputs may be accepted and stored in the memory of the computer, and processing statements are then written, which are then executed one by one to generate the desired outputs, which are also the resulting outputs are also stored back in the main memory of the computer. And finally, the output statements are meant for showing the generated outputs. And this completes the sequence logic structure. That's why we have shown here N. Now, how to implement this logic structure? We shall discuss this now. To implement the sequence logic structure in R in the simplest way, we need to know how to accept input from the console, how to process the stored data, and how to show the output. The simplest input statement to accept input from the console of the user is to use a system-defined function shown below. It is the function is what readline function, and we write the statement in this way. First, we write the identifier. It is then followed by the assignment operator, whatever operator we like. Then it is then followed by the readline function, followed by a prompt equal to any text that we may like to display. The word prompt may also be omitted. Only we can show the text that is to be displayed to make the user understand what input is to be given. If the user tries just to check the functioning of readline function, in that case, the user may also omit this text. So readline function can be directly used without using any prompt or text also. For example, we can write this x equals to readline within bracket prompt, enter your name here. So on display of the string in the prompt, anything the user types followed by the pressing of the enter key will be stored in the identifier as x as a set of characters. The prompt string can consist of a maximum allowed length, normally 256 characters, but can be changed in the source code. This function can only be used in an interactive session. If the data comprises digits, it can be converted into a numeric data as follows: y equals to as.numeric within bracket x. Now we can utilize the value of y to perform arithmetic computations. So let us check this check the functioning of readline statement in our environment. So I would like to show you how R is loaded by clicking on the icon for R, and this is the icon for R. Let us load this. It is taking some time to load. Now it has been loaded. So let us write the statement with the readline function. So x equals to readline, readline. It may you may not be able to visualize this clearly. So I would like to increase the size of this prompt. So now I think it is visible. Readline, then we write enter your name, say here. Then we may generate an arrow sign using equal to and this, followed by space, followed by quotes. So let us execute this by closing the bracket of the function, parenthesis of the function. So we press enter. So it shows this, enter your name here. So suppose my name is ABC. So I write this name. So it's okay. So now you see the name is stored in X. If we type X at the R prompt and press enter, it will show the name stored in X. Okay, let us go back to our PPT. Now, an alternative to the above statement is the use of another system-defined function, scan, to accept one or more inputs at a time in a numeric form directly. To show any prompt string with this statement, we may make use of the cat function to include any desired text of length not exceeding 256. The syntax of scan bracket in its simplest form for getting input from the console is shown below. Variable name, where we want to store the value typed by the user. Then our assignment operator is to be used. It is followed by the scan function. And within a pair of parentheses, we can optionally write n equals to some integer. Here, the optional parameter n equals to integer value implies how many input values the user wishes to input from the console. In the absence of the parameter, R assumes no limit to the number. It also ignores invalid inputs. If the value of n is greater than 1, then R creates variables with names, variable 1, variable 2, and so on, depending on the value of n to store the different inputs. Finally, it shows how many values have been read with the message like read 3 items. To illustrate the use of this format of the syntax, we write the following. Cat, what is your age? We use here n equals to 1, x equals to scan n equals to 1. On execution of these statements, what happens? It shows this read 1 item, and let us see this in our prompt. Let us write age equals to scan. Oh, before that I should use cat. What is your age? Suppose this question is asked. What is your age? This is the prompt. Any text we can include within double quotes or single quotes under cat function. So we write it, we press, we can press enter here, or we can write two statements side by side by separated by semicolon. How? Let me show you. A semicolon, we put a semicolon here, then we write, say, age equals to scan n equals to 1. That means we want to accept only one value. And that will be stored in age. So two statements are here, two instructions are here, are instructions which are separated by semicolon. So if we press enter, I will execute the instructions one after another. Let us see what happens. What is your age? It is asking for the age. Let me write something, say 55. And so it has read one item. Actually, when a scan is executed, actually it accepts the data after this prompt, and it shows read one item. If we don't want to show this message read one item or two items, we can write in a different way. Age equals to scan within bracket n equals to 1 U I E T, white equals to true. True can also be represented with capital T. Okay, so let us execute this. It is now waiting. So let us now enter a different value, 65. So it has not shown any message. Now, if we type age and press enter, it shows what? 65 that I have entered just now. So we have understood how to accept numeric input and how to show some message, that will prompt the user to enter some data value. So I have shown it quite equals to true if we don't want to see that message. The scan function can also be used for accepting console data of all other data types by including a third parameter, what, as shown in the format below. R variable is where the value will be stored, followed by R assignment operator, followed by scan, and then n equals to integer value, y equals to true, what equals to data type function. The data type function may be logical, integer, complex, etc., character, etc. By default, it is numeric. The process statement is nothing but an assignment statement, the format of which is R variable, followed by R assignment operator, followed by another R variable or expression or formula, which is to be evaluated to generate the result or output to store in the target R variable written on the left-hand side. For example, if we write perimeter is equals to 2 star pi star radius, we know that asterisk or star implies sign of multiplication. Pi is a constant, mathematical constant whose value is available in the system R. So if we write pi and radius must be given as input from the terminal, or it must be some value must be stored in the name variable radius, then we can write some variable name, say perimeter equals to 2 star pi star radius, that will take the product of these three and store the result in perimeter. And we can print the result by writing just print identifier or CAD identifier. Print can also be written with some text. In that case, we have to use another function that will include identifier followed by text, identifier followed by text, and all these will be under paste. And before that, outside of that, we need to write print. But more easier option will be this: cat followed by text followed by identifier. For example, here, let us see here, cat the given age is, say, put a colon to space, end of double quotes, followed by comma, followed by age. We write this. So let us see what happens. It shows what the given age is this. When prompt comes here, because actually this cat function does not indicate any end of line. To indicate end of line, we have to use some control character for that. How? Let us write this, copy this here. So after this, we write within quotes, double or single quotes, \n to imply end of line here. So end of line, it will start the prompt from a new line. So let us press enter. We see that the output is shown. The given age is 65, and the prompt comes to a new line, and the fresh one. So this, if we want to use print, we have to write in this way: print. Then comes the paste, PST, the given age is, say, colon followed by some space, followed by this, comma, then age. Actually, paste function does what? It actually concatenates or combines this text as well as the value of this variable. This is the task of the paste, and it is after combination of these two, it returns the result to print, and print executes the command. So let us press enter here. What do we see? What do we see? Oh, I'm sorry, I have forgotten to include the given ages, include this text within quotes. So let us write it again. So if you commit any mistake here, it will show errors. Here is the mistake. So the given age is this age. Now let us put this. So This is another mistake. There are two startup parentheses, one for print, one for paste. So I have only completed only one. The first parenthesis, that is the closing parenthesis of paste. So I have to execute this, I have to close the parenthesis of the print function. When something is not completed and without completing the, if we press enter, waits for the completion of that command. So it shows the plus sign to add the remaining ones and waits for the user's typing. So here I have completed the typing and press enter. Now it shows the result. So what is the difference between print and cat? One difference that we can note easily is that in print, there is a next new line function. New line is inbuilt with the print command. That is, after execution of print, control comes to a new line. Here, there is no need to use the \n as we have used in case of this cat function. Another difference is that in case of print, we need to use the paste function. This is additional thing. Whatever is the choice of the user, we can either use cat or print to print something. Okay, let us go back to our presentation. Here we write this is this. There is another important difference between print and cat. I have already stated the difference. So, I need not specify these things. To get the print with cat, to get the effect of print with cat, we need to use \n that I have already shown practically. Okay, so now let us write an R program to determine the area and perimeter of a circular plot. We can write requisite instructions one by one at the R prompt and execute each instantly to obtain the result of execution interactively. Alternatively, all the statements can be written in an editor by selecting New Script option under the File menu option of the base hub of the RStudio, and the statements can be executed by run all option under edit menu if there is no input commands in them. In case of input statements, the inputs are to be accepted first by selecting them one by one to get them executed by choosing the option run line or selection under the edit menu. Then the rest of the commands are to be can be executed by selecting all of them together and then selecting run line or selection. We can also execute all the statements in one go by enclosing all the statements in a pair of braces and selecting and then selecting run all option under the edit menu option. There is still a fourth alternative in which we save the set of statements in a file with a desired file name, and then the entire set of instructions is submitted for execution in the batch mode by issuing the command source, path name, file name at the R. So to make it understandable easily, let me show you the statements one by one in R. So we select file option, new script. New script is selected. Now let us write the commands one by one. Cat enter radius of the circular plot, because we need to find out, we need to write a program to find out the area and perimeter of a circular plot. So we write this, enter radius of the circular plot, press enter. Nothing will be executed because we are in the editing mode. So next, after this command, say R is the location where you want to store the radius, and we use the scan function to access the radius, n equals to 1. we can also use quite equals to 2 if we like. Okay. Then after this execution, what happens? We have got the radius. Now we can calculate the perimeter, say perimeter, and store the result in P. Say so P equals to 2 star pi. 2 pi is the formula we know to obtain the perimeter. 2 pi r. R is what? This R where we have the radius. Next, we calculate what? Area. Area, let us take A to store the area. The formula is what? Pi r square. Pi is pi pi, followed by star, followed by r square can be easily obtained by multiplying r star r, r into r, pi r square. So you have got perimeter as well as area. Now, we can show this by using the cat command. In this way, the area is, say, put a colon, put a space, say the value is A, and we want to show the perimeter also, and the perimeter is, put a colon, then space, P, comma, P is the perimeter, then we use backslash n to take the control to the next line. After that, we need to close this parenthesis. So this completes our command. So we have come back to the next line. This shows all the commands here. End of the program. We can save this in a file, say save option. And let us write this circle. Circle underscore area. We can name in this way. Circle underscore area. It will be saved with dot capital R extension, circle area. So circle underscore area is the name of the file. Okay. Now we have saved it. Now there are a number of ways to execute this option. One way is this, as I have described. First, we select these two. First way I shall show you, or we shall run the commands one by one. This is the first command. Let me copy this and go to the console. Here is the console and file of editor. So we go to the console. We now paste it in the console and execute it. Enter radius of the circular plot. This is shown and control comes to the next line. So let us go back to the next command. It is this to accept the command. So let us copy this and go back. The Windows, we select our console and we execute the scan command. Press enter. It is waiting for the input. Let the radius be 23.5. So we press enter. It shows no message, but it comes back to the prompt. So next we go back to the next command. We have written all the commands one by one. So we go back to the next command, we go back to the editor. Now we copy this command and execute it. This is for execution. So I'm sorry, I have to go back to the console. So we execute this command. It has been executed. Now let us go back to the editor again. We execute the next command, copy, and we select the console and execute it. It has been executed. Now, again, we go back to the editor, our editor, and copy this command for execution. copy, then our console, paste. You see, bracket has not been copied. So let us complete the command and press enter. So it is showing the area is this and the perimeter is this, and control comes to the next line. So this is one way. One by one, we can execute the statements at the output. This is the nature of the scripting languages. Now, this is an interactive mode of execution. We can also run it in a different way. What is the different way? Suppose we put here, we execute first two commands. We accept the input first. So how to execute these two commands? We go to the edit option and run line of selection. Option is selected, then it is executed. Let us check it whether it has been executed or not. Our console, you see, it has been executed and it is waiting for the input. So let us give some info, 21.5. So it has been executed. Radius has been accepted. Now, after that, we go back to the editor and we select the rest of the commands because there is no input statements here. We select rest of the commands, copy. You need not copy them because we have copied them earlier. Oh, there is one, the one bracket was missing here, I think. Let me show the bracket. Oh, bracket is there. Okay. So let us, okay. So we write edit. Now lines, run line of selection. All commands have been executed. This command, and this command. How to see the result? And let us go back to the console to see the results. You see, this is the result. Where is this? Windows, this. We have selected this. Now edit, run line of selection, then Windows, console. Unexpected string. Oh, there was a cat. What was there? I think the bracket was not copied here. Double quotes have been included. Let us check this. What is it there? There may be errors here. Anytime you may face errors, we start the quotes here, end here. Let us omit this space to shorten the line. Okay. After this, there should be a comma because we are starting another string. So then the perimeter is this. Okay. So we have written this and the perimeter is this. So let us copy all these commands. Okay. Now edit, run line. Let us see whether they have been executed or not. Yes, they have been executed one after another. The area is this and the perimeter is this. Another option, let us go back to the editor to show you the first option. No, another option. We enclose all the statements within a pair of braces. Let me reduce the size a bit, otherwise we cannot accommodate all these things within the screen. So we have reduced the size, okay? So by reducing this size, closing of parenthesis, then we type the closing brace. Closing brace is there, opening parenthesis is there. So now we select edit option and select run on. What happens? Let us go back to the console. When we use run all, it is now asking for the radius. Say the radius given is 31.67. Okay, so it shows the area and this. So we can also execute the set of commands by enclosing them within a pair of braces. Now we have given some name to this program, circle area data. So the last option of execution, last way of execution is this. We write the command source bracket within quotes. Path is the current path. It means path is not given. Circle area, circle underscore area dot r. This is the command. This is the file name. So we write it within quotes and close the parentheses. This command will load the file from the secondary storage medium where we have stored the file, and it will execute the statements in a batch mode one after another. So it is asking for the input now. Let us enter 16.9. It shows the area as well as the perimeter. So this is how, I have shown you a number of ways in which a program can be executed. So let us go back to our presentation. So this is the program. We can write something, we can print like thank you, etc. And I have shown these statements also. Let us, we have completed the first program, and I have also shown you how to write statements one after another, separated by semicolon. All the commands can be written in a single line also, like this, in a single line for execution. If we press, execution will be done by the system. We can also change the path in a number of ways. We can get the current working directory by using the getWD function. It shows a directory like this one. What is the current directory? And we can change the directory to some other way, to some other new directory of our path. We can set some new directory also, setWD, by using the setWD command. For example, if we want to put all our programs under our programs directory, then we can write in this way, setWD paste 0, get bracket /r programs, all in a very simple way. In this way, get working directory is this, set working directory, the new directory name, and we can again use getWD to check whether the working directory has been changed in this form or not. Now we can execute this source circle area data as I've shown. So let us take some other example. Write a program to determine the volume of a rectangular box. We know that the volume of a rectangular box is the product of what? Length, breadth, and height. Let us use n equals to 3 in scan command. We give this message and we write n equals to 3. So the values will be stored in 3 variables. One will be named as x within square bracket 1, x1, x2, and x3. And what will happen? And we can make use of these variables to get the product of these 3 values to get the volume in B, and we can show the volume there. And similarly, the prompt will be shown as I showed earlier. Yeah, this is another program to develop. This is the program to obtain the area of a triangle. We know that if the lengths of the different sides of a triangle are given, say A, B, and C, we can find out S equals to A plus B plus C by 2, half of the perimeter. Then ABC at the lengths of the sides, and we can obtain by using the value of S, where we have stored A plus B plus C by 2, by using this formula. For getting square root, we can make use of our library function is keyword T, and we put the values there. So we can use another formula, base into altitude by 2 if the altitude and base both are available. So we can make use of any of the algorithms and we can calculate this result. Another problem may be considered, for example, if P amount of money is invested for n years at a rate of interest I compounded annually, the money grows to an amount T, it is required to develop a program in R to determine the value of T. So, you know, P, N, I, and T, these are, as described in the problem, are required as inputs. So we can P for principal, I for rate of interest, annual rate of interest, and N for number of terms in years. So we can put the values in the formula in this way to get the result. Let us take another example. It is required to develop a program to determine the volume and surface area of a sphere. We know that the formula is 4 by 3 pi r cube. So if the where I is radius, pi is the constant, mathematical constant, whose value can be obtained by using pi, as we have seen earlier. So if we know the radius of the sphere, we can easily determine the volume by using this formula. So the program can be written in this way: enter the radius of the sphere. We have used scan here to get the radius. Then we have put the value of the radius here in this formula, and we have obtained the here surface area is obtained in this way by using this formula 4 pi r square, and then we can we have also obtained the volume U in B. So we can show both the things. Now it is required to develop R script to interchange the values stored in any two R variables. So in this case, we can make use of this logic. Suppose A and B are the variables where we have stored the values, and we can make use of this logic by using these 3 steps. You can interchange the values. A equals to A plus B, B equals to A minus B, A equals to A minus B. So we get these values, interchange values. Similarly, the employer of a firm issues the employees of a yearly payment of an amount P after the retirement until he or she dies, assuming a fixed rate of inflation of R% per year and the expectancy he of his or her life, the set of steps required to calculate present value of the total payments from the employer is to be determined. This is a problem of determining the present value of an annuity, where an annuity is a fixed sum of money paid to someone each year, typically for the rest of his or her life. There is a present value of annuity formula to determine the value of a series of future periodic payments at a given time. The present value of annuity formula is based on the concept of time value of money. In that, 1 rupee of present day is worth more than that same rupee at a future date. So this is the formula for that. PV stands for present value equals to P present value 1 minus 1 plus R whole to the power minus N, whole thing divided by R, where P is the periodic payments and R is the percentage rate of inflation or discounting per period divided by 100. N is the number of periods. So if we accept those values, enter the age of retirement followed by life expectancy, we can expect these two values. And that's why you have given n equals to 2. How long the person may live, that is the life expectancy, and amount of annuity followed by the rate of inflation we have accepted. In another step, then we have used the formula to get the result. And a program in R is required to be developed to calculate the EMI effective loan amount. If we take loan for some purpose, for purchasing some property, we can find out the EMI of the loan by using this formula. P is the principal loan amount, R is the rate of interest, and that is calculated on the monthly basis. So this is the formula, R into 1 plus R whole to the power n, where n is what? N is loan term divided or tenure or duration in number of months. And so we can put the values in this formula and we can get the result. Inputs can be scanned and the values can be put in the formula to get the desired result. An R script is required to be developed for evaluating the yearly amount of depreciation on any asset value. What is depreciation? We know that depreciation is a reduction in the value of an asset over time due to its wear and tear, in course of its use over time. Straight line depreciation is the default method used to gradually reduce the carrying amount of a fixed asset over its useful life. The method is designed to reflect the consumption pattern of the underlying asset over time. Under the straight line method of depreciation, we distribute the depreciation expense evenly over the estimated useful life of an asset. The straight line method calculation steps are as stated below. The initial cost of the asset that has been recognized as a fixed asset is determined first. It may be buying price of the asset. It is called the cost of the asset. A value called the salvage value of the asset is then estimated, which denotes the value at which the asset can be sold out at the end of its useful period. In other words, salvage value, also called residual value or scrap value, is the estimated value of the fixed asset at the end of its useful life. The useful life of the asset is then estimated. And we use the formula cost minus salvage value divided by useful life in years. So we accept all these values and put the values in the formula that we have written here. This is the formula, and we can obtain the depreciation amount. This is in using the straight line method. This will be same for all the years. Finally, let us consider a relationship between the three standard scales, the scales of temperature, namely centigrade scale or Celsius scale, Fahrenheit scale, and Reaumur scale. And the relationship is given by this, where C stands for Celsius or centigrade scale temperature, F stands for Fahrenheit scale temperature, and R stands for Reaumur scale temperature. It is required to develop a program in R to convert available temperatures in the Celsius scale into its equivalent temperature in the other two scales. So the formulas are very easy. From the equations, we can obtain F equals to this and R equals to this. So we obtain the input and temperature in Celsius scale and put the values in the formula to obtain the equivalent temperature in Fahrenheit and Reaumur scale. So the outcome of this lesson, the committed outcome of this lesson are the following: the features of a programming language, the concepts of assembler, compiler, linker, loader, source module, object module, and executable module, the concept of an interpreted programming environment, the features of structured and unstructured programs, the basic concepts of top-down programming approach and modular programming, the program logic structures used in a structured program, and some illustrative examples of with the implementation of the sequence logic structure. This completes my second lecture on R programming. I hope you have understood this deep thing, and let me end this lecture for today.